this video, I will be showing you how to construct the velocity diagram for question 2 of your problem set. To complete this diagram, you're going to need a ruler, set squares, pencils, a good eraser, sharpener, and of course your calculator. So let's get started. The question says, the mechanism of a warping machine has the following dimensions. These are given in millimeters and they are the lengths of your links in the mechanism. The crank OA rotates at a uniform speed of 100 radians per second in the clockwise direction. So O is fixed, A is rotating. You can see the arrows are showing the direction of rotation. And we're asked to find the velocity diagram and point P. So we're always given a suggested scale as well as your starting point. The starting point combines all the fixed points in the mechanism. So we have 1, 2, 3 fixed points. So they are all combined at the starting point. To start constructing our diagram, we have to find point A first because that is the information that we are given, and so that's our starting point. We have the speed of 100 radians per second, so that would be the angular velocity of the link OA, and we can convert that to velocity, so equals omega times the radius. So this would be 100 times the length of the link, which would be 0.1. Again, I've converted it to meters to keep it in standard units. So this is 10 meters per second, and that is the velocity of A relative to O. So now we need to apply the scale. Our scale is 1 centimeter to 1 meter per second, which means this line is going to be 10 centimeters in length, and that's our point A. So let's discuss the direction that it's going in. A is going clockwise about the fixed point O. So if we're going in the clockwise direction, if my point is fixed, we're going clockwise, the velocity has to point down to get that clockwise rotation. So from my starting point here, I draw a line perpendicular to the link OA, 10 centimeters in length. Line your ruler up against the link, put your set square against your ruler. That line is perpendicular to the link OA. I know my line is going down, and then I know my line is 10 centimeters. So measure this accurately as you can, and this is point A. Add your label, and your arrow indicating the direction, so velocity A relative to O. So that is our first point on the diagram. Let's find the next point. Back to our mechanism. We have point A that's connected to point B and point C because they're on the same link. Our next point that we're going to solve for is actually point C. This is because C is connected to a fixed point, O3. So this will make it easier to solve. If you choose point B, you'll have to draw about 4 lines until you find that point. So if we choose point C, just like before, we only need to draw 2 lines in. So we're choosing the next easiest point to solve. Velocity C, that means we need a relative equation. So velocity C is our unknown, that's on the left-hand side of the equation, equals velocity A, which we know we have to use that point because we have to have something that we know in the equation, plus C relative to A. So I'm drawing in 2 lines, velocity C and velocity C relative to A, to find where they cross, and that's going to be point C. Take my ruler, take my set squares, velocity C relative to O, my line perpendicular to the link CO, and then that line will be going through my starting point. I don't know the length, I'm going to extend it, but I don't know the length or the direction. I only know the location and that it is perpendicular to the link CO. Now I have my other line, so that would be the link CA. So ruler against the link, I put my set square against the ruler, and this time I'm starting at point A because A is what I know, C relative to A, draw my line, and where they cross, this is point C. So before I do anything else, I'm going to erase the extra lines. I'm going to make sure we can see these velocity lines very clearly, and then I'm going to add my arrows and labels. So this is the velocity of CO, and this is velocity of CA. My arrow points up towards point C and away from point A. Now, what's our next point? So we have point C, we have point A, we need to find point B. Point B is on the same link as C and A, so we can use a ratio as we've done before. If they're on the same link, they have the same angular velocity. If you look at the velocity diagram video for question 1, you will see how I determine the ratio equation. But here I'm going to just say velocity of CA on velocity of BA equals the radius of CA on the radius of BA. B is my unknown, so keep that on the left hand side. BA equals the velocity of CA multiplied by the ratio BA on CA. I know the length of velocity CA because we have that point. So measuring the line in your diagram, C relative to A, so this will be about 7.9. BA on CA, I'm going to use my ratio of the lengths of links. So BA I can calculate from what's given, so this will be 500 divided by CA, which is 700. I don't have to convert those to meters because I'm using a ratio, so the units will cancel each other. So if I do this calculation, 7.9 times 500 divided by 700 equals 5.64 centimeters. So remember, this is velocity of B relative to A. So on my diagram here, I have C relative to A, I want B relative to A. So I measure from point A, 5.6, and point B is here. And then I have my velocity of CA link, I will label there, and then I'll keep this as BA. Before we move on, we're going to draw in the absolute velocity, so velocity of B relative to O, your fixed point, and checking I have all my arrows and labels. So looking at point B, now we can move on to the next point. B is connected to point D. If I have a new point, I need a new equation. I'm going to use a separate page. Velocity of D equals velocity of B, which we know, D is our unknown, plus velocity of D relative to B. Drawing both of these lines, seeing where they cross, and that is going to be point D. On our diagram, we have velocity of D relative to a fixed point, O2. My line will be perpendicular to this link. Put my ruler against the link. I have my set square against the ruler, and then this line. I don't know the length or the direction, I just know that it's perpendicular to the link DO. And then my second line is going to be perpendicular to the link DB, going through point B on my diagram. So we'll draw it from this side. Ruler along the link, and I'll extend this line here, going down, and here we have point D. Removing the extra lines, labeling everything, arrow, velocity label. So I'll go over this one again. This is my absolute velocity of D relative to the fixed point. This is my velocity of D relative to B. Our last step is to find point E. So if we look at the mechanism here, E and D are on the same link. It's an L-shaped link. So imagine this link here. This is point D and this is point E. So if D is pointing downwards for velocity, then E is going to rotate at 90 degrees and be pointing towards the right. So I have my L link. You can see on my diagram, D, velocity of D is pointing down. So my link is rotated 90 degrees, and that means velocity of E will be pointing at a right angle to velocity of D because we're on an L link. But before we can draw that in, we need to know the length. D, E and O are on the same link, so they have the same angular velocity. Let's do a ratio. Velocity of D equals velocity of E, radius of D on the radius point E. Velocity E is our unknown, so that is on the left hand side, and velocity of D multiplied by the radius of E on the radius of D, and this is of course relative to a fixed point. Velocity of D we measure from our diagram, so this is D relative to our starting point, so this is 1.9, shall we say? Oops, there we go. 1.9 again in centimeters. And then our ratio of the links of E is going to be 400 divided by 200. So it's 2 times the ratio. So this will be 3.8 centimeters. Of course, because this is a graphical method, all our values will be different, but if you follow the method of constructing the diagram, we should get something quite similar. So this line should be about maybe 3.5 to 5 centimeters. So what did I have about here? So this is point E. I write in velocity of E relative to O, remove my extra lines. And now the question was asking velocity of E, so you need to measure that line, remove the scale, and then that will be the length. The velocity. Again, if you were asked to find angular velocity of any point, the calculation would be velocity on the radial length, and then you need to state the direction. So to do that, if we had D relative to B, that means B is my center of rotation here. So D is moving about point B. I pick up the line DB, move it to point D, and see which direction it's rotating about point B. So that would be in the counterclockwise direction. So my angular velocity of dB would have to have a counterclockwise direction in your solution. Okay, so this is the velocity diagram for question 2. As I have done before, I've shown all my working. I have 2 relative equations. I have a ratio calculation for the 2 points, and I have my label diagram with the letters, arrows, and velocity labels. So next time we're going to construct the acceleration diagram for this question as well.